All right. So we're at class 35, and we only go through 40 for the semester. So we're really getting pretty close to the end of things here, folks. The last of your WMS assignments is due on Wednesday. And today will be the last of the class meetings that we have devoted to WMS. And so you'll still need to have the program available for the final exam, but we won't be doing any more assignments or in-class demos with it. So like I just mentioned, today's class is going to be an illustration of what we can do to set up a model for HEC-HMS. And HEC-HMS is software that's made available by the U.S. Army Corps of Engineers, and it's what they use for watershed modeling. It is able to execute models, but it doesn't have some of the same GIS tools that WMS does. And so HEC-HMS has a few strengths that WMS lacks, like HEC-HMS is good for multiple basins at the same time in a way that maybe WMS doesn't have that same kind of horsepower to keep track of different elements in a project simultaneously. But it's not so good for automatically calculating curve number and defining precipitation on the basis of a single click and all that. So I'll illustrate that to you today. Are there any questions about the course in general or schedule related things before we move on? Josie?
You said 331 is canceled on Friday. Is this one too?
It's not canceled, it's moved online. Yeah, so Friday of this week and Friday of the following week, our class meeting will be just posted online. So we won't have an in-person live meeting for either of the remaining Fridays. Thank you for reminding me of that. Are there other questions? Let me just put it on here to make it official. All right. I don't know why it insists on retaining superscript, but now that looks good. All right. So the watershed we're going to look at today is close in proximity to the watershed we looked at on Friday up near Barker's Ridge Road in Milton, West Virginia. And we're going to use that as an example, this Jenkins branch, as an example of two main things. First of all, how to set up a HEC-HMS model, but then also how to compare it to HEC-1. Because sometimes when you tell people that you're running a HEC-1 model, they'll look at you like maybe you're using old technology, but that's simply not the case. From a hydrologic perspective, the calculations are the same, whether you execute a model that's a HEC-1 model or a HEC-HMS. It's just HEC-HMS is its own standalone software. So I hope to illustrate that point today, is show you that you get the same flow rates whether you do it with HEC-HMS or HEC-1. But for us to do a HEC-HMS model, we have to open up a second software package, which I'll illustrate for you. But to begin, let's start with WMS and identify the watershed that we're going to use for this illustration, Jenkins branch. So like we do, we'll start with the Hydrologic modeling wizard. And I'm going to just browse to a location that you kind of especially want to be clear on where you're working today, because we're going to have to open up these files with the external software, the HEC-HMS software. So I'm going to create a new subfolder, one that's called HMS model, and then later I'm going to have one that's called HMS export. So the model is the stuff that I'm creating with WMS. So this is Jenkins branch. All right, so I'm already on the location because I was in here earlier. So here we are in Cabell County, and it's going to be just kind of north of Milton. Here you can see the parallel lines of that unusual watershed that is south of Jenkins Branch And then this straight channel here, Jenkins Branch itself, is what we want to delineate. And what I'm interested in, if we zoom in, we can see that Jenkins Branch and another stream come together and then go under Swan Road. So I want to capture the combined flow of those two streams together. So when I go to drop my outlet, it's going to be a couple of pixels downstream of where these two branches come together. But I want to make sure that I have the entirety of the contributing area for those two. And at this, I think I've got it, because I'm going as far west as this branch is excluded, and as far south, I think with this other stream, it's going to pick up an area down here. All right, hopefully I've got the whole area. Now we're going to get the three files that we usually do: the elevation, land use, and soil type. And at this zoom level, I think 15 meter is the DEM resolution. It's going to download. Gets the soil type. It probably will pick up 3 different counties of soil type data just based on the proximity to a few borders. You can see we've got 3 different counties of data. We don't need this one. The way that we can tell right away that we don't need it is that the DEM file isn't visible once we turn that soil data off. So this 600 we don't need, the 79 we don't need, but this 11 is Cabell County, and that we do need. All right, I'm going to save the data just to make sure, in case there's a crash, that we can come back to this point. Okay, so who knows what we do at this point? Like in the workflow, where are we at? I mean, we don't necessarily always have to do things in the same order, but what still needs to be done?
You can join the NRCS.
Okay, we're going to join the NRCS,
New coverage.
create a new coverage,
Delineate a watershed.
delineate a watershed.
Shape mapping.
We need to map from the GIS data into the new coverage. And so in delineating the watershed, one of the subtasks there, of course, will be running topaz, dropping the outlet. So let's do that first. Let's go to compute flow directions and compute topaz. Now, I want to make a point. When I was looking over some of your files for the exam, some of you had such a small area for the minimum flow accumulation threshold that basically your whole map was a sea of blue, that all you were seeing was flow accumulation cells. So let me just show you, like, if you do that, what things are going to look like and then what they ought to look like. So if I have this down to 0.5 acres and I compute topaz, then there's going to be way more blue cells. I mean, in some cases, let's see, 0.1 acre. All right, see how it's just all blue? So it thinks that there's streams everywhere, because what we're saying with this 0.1 acres is that all it takes to have a stream begin to form is 0.1 acres of upstream area. And what makes it tricky if you have this much blue is picking out where the stream really is and dropping the flow accumulation cell in the right spot. And so my suggestion is that if you have a general idea of where the watershed is, and you typically will, simply because of looking at the project site when we were setting the boundaries of it, or if we do get online maps, you can sometimes get an idea of where the ridge lines are and where the stream is based on what you see here. So, you know, it's okay to have the streams extend into each little side hollow, but you don't want to have so much that you can't see anything else because you've got so much of the blue shown. All right. So here's the crossing under Swan Road. So I'm going to pick this flow accumulation cell because I don't want there to be any confusion about maybe it's splitting it into 2 different subbasins or missing one of them. So this pixel on Jenkins Creek will serve as a proxy for the flow that's going under the road there. And so the contributing area, if I go a couple of pixels downstream, is maybe going to be like a quarter of an acre too big, probably even less than that. But I don't want to mess with, if I put the flow accumulation cell here, it may split it into two watersheds or only get one of them. Okay, so I've dropped that outlet and delineate, and let's see what we've got. Hopefully, oh man, that's embarrassing. Flat lines across the top. Oh boy, when will I ever learn? All right, let me start over. See how quick I can do it this time. Maybe speed is the problem. All right. All right. Maybe this will be more like it. Let me delete this unnecessary soil data just to keep the system from getting too bogged down. The more that's there, it's just going to be using RAM if we've got a lot of unnecessary soil data shown. All right. Let's compute topaz. Turn this off for now just so that I can drop my flow accumulation cell. The outlet here. Now I'm feeling shy about whether that's the right spot. I guess I better bring up the map just to make sure. Yeah, that's it. All right. Fingers crossed now. Oh, man, just barely. Boy, oh boy. All right, so 1420 acres. This is a pretty big watershed. All right, so some of the steps that were mentioned a few moments ago, we have to right-click and join NRCS data. We're going to fill in the blank values with D, just for a worst-case scenario type coverage. And speaking of coverage, we need to create a new one. Soil type coverage. All right, and select the polygons that are inside of our watershed and copy them over into the soil type coverage. And we can see that it looks like we've mostly got type C soil in this watershed, a little bit of type A soil. So none of them are those assumed type D soils that we said that would fill in any blank spots. Okay, now that that's copied over into the soil type coverage, we can see them here because that's what's active in the map. I can switch that off. I mean, it's still able to do calculations with it, it's just maybe a little bit less visually distracting if it's not displayed. We can go into the hydrologic modeling module and use the calculator to compute the curve number. I need to import that text file that explains the relationship between land use, soil type, and curve numbers. And it runs the calculations and gives us the composite curve number for this watershed, which I think is maybe around 68. 67.66. Okay. Now, if we wanted to do a HEC-1 model, you can see by default it's assuming that's the model we're going to use. We would just double-click on the icon and start filling in the data here. But instead, we're going to do HEC-HMS. So I want to save my work up to this point, just in case things crash, so I can come back to it. So I'm going to click on Save again. Okay, so all of the files that are associated with this project are right now in this subfolder HMS model, which I just created, and so we can see the soil type data is there, the WMS file, a few other things having to do with the land use, the soil type, and so on. Geo-referenced image. But instead of HEC-1, pick the drop-down box, and we're going to choose HEC-HMS. Okay, now under the HEC-HMS drop-down, we have job control, parameters, and meteorological parameters. So job control has to do with the timing of the model. Like, you have to tell it, if you're doing a simulation, when its simulation should start, when the simulation should end, and then at what frequency or what duration is like the time step calculations. And it can be it could be the actual date of some storm that you have rainfall data for. So like if you're doing a historical storm, you could say, I want my simulation to begin June 3rd, 1927, or whenever you have this rainfall data for and whenever you're trying to simulate. Or it could just be more hypothetical, then it doesn't matter so much the start date and time, except for one thing. The starting time and the ending time should match up so that it's on the same time interval frequency that you're saying down here below. I ran into an error message earlier when I didn't have that matching. So let's say, for example, we wanted to go from 12:15 and 00 seconds on April 11th until 12:15 and 00 seconds on April 12th. And so this is going to be a 24-hour simulation with 15-minute time interval steps. Okay. We don't have to put anything into these tabs for the most basic kind of a model, but you could define things like snow melt, evapotranspiration, but we're not going to do that. We're just going to go with these default options, but we did adjust the timing of the model. Okay, so that's the job control. Set that. Now here under Edit Parameters, we're going to define a few of the things that we would have told it in HEC-1 as well. It's just that there's a different name for it. Loss rate is where we're going to tell it what approach it should use to transfer between the rainfall depth and how much of that is rainfall excess. So, for example, we've used the NRCS method, which is based on curve numbers for our loss rate on all of the HEC-1 models that we've done. So if you tick the box here for loss rate, then it gives you the option of choosing what approach you want to use for the loss rate method. So by default, it's assuming down here in this properties box that we're using SCS curve number. So check that box for SCS curve number. For transform, the transform is the temporal distribution of the rainfall excess. And so it's going from the depth of runoff to its occurrence over time. So the transform, in other words, is where you're telling it to use a unit hydrograph. And so we'll use the SCS unit hydrograph method for that. And so there's some fields in here that down in the properties we're going to have to calculate or specify in a minute. And then finally, base flow is answering the question, do you want to account for water that was in the stream before this current storm event occurred? So let's turn on base flow just so we don't get an error later on. But the default assumption is that there's no base flow to begin with. And so if we happen to know that there's 10 CFS in this channel before the storm, we could add it on in the simulation, or we could just, in our minds, once we've calculated the storm's peak runoff, we could add on any base flow that we know about on top of that. Okay, so we've specified those three options, and then down here in the properties box, let's check on what it's understanding about the SES curve number. So it takes the 67.66 that we calculated earlier and it automatically fills that in. Now, we don't specify a separate initial abstraction. You'll remember that the default assumption for initial abstraction is 20% of the storage. If you happen to have a really well-calibrated watershed, you can tinker around with the actual initial abstraction. So there could be watersheds with just an enormous amount of leaf litter, and so the initial abstraction is more than 20% of the storage, where storage is based more on the soil properties, but initial abstraction is things that are above the soil. So you could make adjustments to the initial abstraction, manual adjustments, but we're just going to stick with the default that's based on the curve number. Likewise, you could also specify the percent impervious in a watershed if you knew that there was a lot of roof areas or a lot of paved areas or things of that nature. In this rural watershed, it's almost entirely undeveloped or farmland, so there isn't any impervious area. Okay, so now we are in the transform, and the transform method of SES is how we're going to determine the lag time. And so if we click basin data, we get the same dialog box we've seen on other occasions where we can choose from among all the different methods for calculating calculating the time of concentration or lag time. Until now, we've just relied on the SES method because we always have the curve number, watershed slope, and watershed length, and because these watersheds are within the typical parameters for the SES lag time. So click OK, and it fills in automatically the 0.74 hours that's assumed based on the SES method, and remember, no base flow. Okay, so any questions so far on the types of things we're defining for HMS? And by the way, I want to make an important point, and that is the button locations. I mean, that's going to change from version to version of the file. But what I really hope you take away from this class isn't so much like where to click in the program, but what I hope you take away is what sorts of things do we have to define in the program. You know, like what are the hydrology fundamentals that we know have to be satisfied to create a model, and how are we going to tell the program things like how much precipitation there is, the temporal distribution of the precipitation, what it should assume for the amount of infiltration or the rate of infiltration. I mean, those are the fundamentals that if you understand them and you know what sort of information you have to feed the computer, you can still go on the lookout for a particular window if you haven't yet defined a parameter. You know, like when you get an error message and it's an unfamiliar code, you know, error message 1408. You may not even have to look that up if you suddenly realize, oh, I didn't even specify a precipitation depth yet. So you just have to keep in mind, what does the computer need to be able to do a simulation? All right, so click OK. And back up here into the HEC-HMS, what we've done so far is define the job control and the parameters, but we haven't, speaking of precipitation, we haven't yet told it anything about the rainfall. And so we do that in the meteorological parameters. Okay, so here, precip from web, if you click that, it'll use the location of our watershed to identify both the latitude, longitude, and let's do this as a 10-year storm. So we'll get the 24-hour storm duration, 10-year return period, click data, get data. Okay, so 3.602 inches is our midpoint estimate of the 10-year rainfall depth. Okay. And of course, this Haito graph, XY series, is how we define from depth to the temporal distribution of that depth. This is the 24-hour depth, but we want to know when during the 24 hours is this rainfall going to occur. And remember that the type 2 distribution, type 2 24-hour distribution, it's not that every storm has this period of intensity that's about 12 hours after the storm starts. It's not just like every storm in West Virginia has the intense part 12 hours after the rain begins. It's just that over thousands and thousands of storms, this is the distribution that is characteristic of the rainfall behavior in the state. So there can be some storms that maybe are even more intense, where a greater fraction of the storm is in that same short period of time than is shown here. But this is an average distribution. Okay, so now we've got the depth, and the timing of that depth over a 24-hour period is defined. Okay, so we click OK. Now we've defined at this point all of the parameters that HMS needs to execute a model, but you'll see here there is no run simulation option. It's grayed out. We can't run the simulation from within WMS because HMS is its own program. It's not just a model, it's a model processor and a hydrologic model. So what we're going to do is save the HMS file. So click on that, and I've so far been working in HMS model subfolder. I'm going to create a new one just so that there's no confusion. This I'm going to call HMS export. And so these are the things that I'm exporting from WMS, and then I'm going to open up in the HMS program. So let me call this Jenkins, since that's the name of the watershed. Save it. Now, it's going to take a while because it's creating a lot of files in that subfolder. I'll browse to them to show you all the things that it's created. So HMS model is what we've been working in for WMS, and HMS export is where we just saved a bunch of stuff. So what it copied over was a run.run file is telling HMS things like the starting time and the ending time of the simulation and how many steps there should be. The .MET is the meteorological data. So that's where it's saying the depth of the storm, the 24-hour duration. The .MAP is kind of a shape of the watershed. So when we open up the program, when we open up HEC-HMS, it's going to be reading a lot of these files simultaneously. And I hope it works because I tried this a couple of times this morning. One time it worked smoothly. The other time it didn't work smoothly, I guess would be an understatement. And I had to manually import each of these individual components rather than it automatically opening everything at the same time. Now, let me just give you an idea. If you're interested in downloading HEC-HMS, it's free and you're not going to have to fight with any kind of license activation. So you can get it. You don't have to get it now, although it does install pretty quickly, a lot faster than WMS does. HEC-HMS download. And another nice thing about HEC-HMS is that it gives you the option of either the Windows version or a portable version. My suggestion would be to go with the current version rather than the beta. But these two different options here, this is going to be installed on your machine and you have to have administrator rights. But a couple of you are borrowing a computer from the library, and so you'd have to go over there to install it. If you don't want to do that, you can use this portable version. And so it's not actually installing the software, but it can just execute it without installing it. Similar, I think there was a similar option with HY8, where there was a standalone, but then there was a portable executable that doesn't have to be installed. So I wanted to point that out. So it downloads and installs pretty quickly, but most of you I don't think are going to have that right yet. So this is the program, and what I'm going to do is just try and open up, browse to the location of that, what do I call it, HMS export. So let's browse on my C drive temporary folder to HMS export, and here's Jenkins.HMS. Now fingers crossed, if this works, what it'll do is it'll open up, okay, first of all, what WMS is exporting it to is version 4.41 of the program, and this is just saying, do you want to convert it to version 4.9 of HMS? So let's convert it. And that's really our only option besides cancel. And it looks like it did import all of the components that I was hoping it would. Because over here on the left side, that looks familiar. You know, the shape of our watershed is familiar from before. And it gives us some new symbology where there's a watershed connected to an outlet. WMS does the same thing when it comes to kind of a symbol of representing a basin and an outlet. Okay, so that's a common way of displaying it. Okay, if we look at the meteorological models, you can see it's that 3.60 inches that we told it about when we were working in WMS has been exported over, along with the type 2 24-hour distribution. Well, I'm just wondering on these basin characteristics. All right, so it knows the area in miles. You can see that the SES curve number is defined for the loss method. The transform is the SES unit hydrograph. So those are the things that we defined previously. Loss 67.67 is the curve number. Transform, we have the lag time that we'd calculated previously. So these basin characteristics were all defined from WMS, and we could do it in HEC-HMS, but if you want to spend a little time outside of class going through the tools that are here, I don't think it has quite the same capacity to go get the soil data for you and automatically calculate the curve number. So it would probably take some additional time to calculate the curve number and to get the precipitation data. Although you can get the precipitation data just from the website. You know, that's not the end of the world, but it's not click it and it gets copied in. Let's double check the control specifications because we want to make sure the timing here. So 12:15 to 12:15. If it is not on 15-minute increments, but our time interval is 15-minute increments, then that could be an error that we might get. Okay, we don't need to do anything with this time series data. Okay, so it's ready to go, ready to execute the model. We need to create a simulation run. So if we didn't already have one, here run 1 is already defined, but we need to right click on it and have it compute. Okay, 100%, it finished computing the run. Now one place where I will acknowledge that HEC-HMS does a pretty nice job is the reports that it gives you. If you look in the results, it has some pretty nice reports. So if we click on the simulation report, simulation run 1, it's got this summary of the peak discharge. So I'm going to write this down on the whiteboard here. It says that our Q peak is 502.4 CFS. 502.4 CFS. All right. So the reason why I write that on the board is just because we're going to pull it up and run a HEC-1 model in WMS to see if it is hydrologically the same. Okay. Let's see. Yeah, so let's look at the basin. So clicking on 1B, which is the basin, it's got a nice hydrograph as well as the rainfall hyetograph. So here is above it the rainfall, and then here's the result of the rainfall excess. So our runoff hydrograph. So that's pretty nice. You can print it. You can edit the graph properties in a way that maybe isn't quite as simple in WMS to change colors of the hydrograph and so on. The summary table, we've seen that already, but here's the spreadsheet data that shows how much precipitation at each one of these 15-minute time increments there's been, how much of it is infiltrated, how much rainfall excess there is, and the runoff. So these reports are pretty nice. We've got different ways of just visualizing the results of the model. And so that's HMS in a nutshell, how you can set up a model. Now the question is, how does it compare to if we had run this as a HEC-1 model? HEC-1 is older than HEC-HMS. You know, back maybe until 15 or 20 years ago, the Army Corps of Engineers didn't have its own software for running hydrologic models. Then they developed HEC-HMS, and it's been improving ever since. And when they did, they decided to just rewrite the code for the underlying hydrology engine, since HEC-1 was written, I think, with Fortran, which is kind of an old computer language that is a little bit clumsy. They converted all of the same basics into new code with HEC-HMS. So let me switch this over to HEC-1, and let's see if we can define the model. So our precipitation, basin average, 3.6, it knows from before, but we need to make sure that we define the series as type 2 24-hour. Okay, so that's all set. Loss method, it knows the curve number from when we were calculating before. Unit hydrograph is defined. Okay, so all the parameters are there. Let's run the simulation in HEC-1 and see if it's about the same 500 CFS peak flow. Okay, it's done, and we'll open up the hydrograph. 500.74. So, you know, obviously that's just, you know, a round off issue where I don't know why, just maybe the different ways that it's slicing time, probably, you know, 15-minute increments. You know, it's as a percentage less than 0.1% different between HEC-1 and HEC-HMS, but yeah, that's basically all I wanted to illustrate for you, is that if you do find yourself in a work environment over at the Corps or someplace else where you're expected to create HEC-HMS models, you can, you know, if you want to use HEC-HMS, you can, but it may be to your benefit to integrate the two, to toggle back and forth between WMS and HEC-HMS. And in fact, once you have a HEC-HMS model within WMS, if I just switch back over here to HEC-HMS, you can read a solution so that, you know, the result of the run 1 that we just did in HMS was the HMS export. So the solution that we got after running the model, this .sol, you could import it into WMS, and so the only thing that WMS doesn't do is execute the model itself. It can be a pre-processor and a post-processor, but it won't do the calculations from within WMS. Any questions about HEC-HMS or how to set up a model in WMS that you could open in HMS? All right, well, that's all I have for you today. Just remember that your final WMS assignment is due on Wednesday. And if you have any questions as you're working on that, just let me know.